All right. Well, good morning, everybody. Today I'm here to, first of all, I'd like to thank everybody for being here today. I hope you guys are all good. And today I'm here to present my research project report, which I give a title to it is Wheat Yield Components and Their Response to Two Different Management Systems. Um, Here I have the authors, me, Dr. Silva, Tyler, Israel, and Abiola. All right, so a quick summary. I'll give an introduction, then we'll move to the objective, experiment information, treatments and experimental design, measurements, results, discussion, and at last, the conclusion. All right, so to begin here, winter wheat in Oklahoma. What type of winter wheat is produced here? So here in Oklahoma, we have the hard red winter wheat, and this type of wheat is used for bread. So the milling characteristics is good for bread. So croissants, hard rolls, and some types of Chinese noodles. Then the state of Oklahoma in the year of 2021 was responsible for 9% of the total U.S. production of wheat. So here in this graph, you can see Oklahoma is in green, and it's the second state just behind Kansas that most produces wheat in the U.S. About 96% of the winter wheat produced here is dryland, and then due to the type of climate that we have here, um, farmers, producers, they choose to use low fertilizers and pesticides, and but they they do not use high rates of these inputs. So yes, as I was explaining, the dry conditions from the state lead producers to choose conservative practices, and this might lead to inadequate use of nitrogen and fungicide. Um, Moving on. So, what is the importance of nitrogen that we're talking about here? Well, for many things. For at first, it is the building block of proteins. So cells require proteins. They need proteins to grow, to multiply themselves. And well, nitrogen is in each amino acid molecule, as you guys can see here. And proteins are made of huge chains of amino acids. So there's a lot of nitrogen there. If you don't have enough protein, nitrogen, you won't have enough protein for the cells to be able to grow, and then the plant won't be able to grow. The tissues won't be growing, and that's going to impact the amount of phosphorylation. The amount of photosynthesis that the plant is doing, right? Then, because you will have less leaves, right? Less biomass. Then what else? Nitrogen is a component of the chlorophyll molecule, which is part of the chloroplasts, where photosynthesis takes place, and that's where plants get their sugars, their carbohydrates from, and that is really important for the plant to grow once again, and also for the plant to allocate nutrients into the heads, into the grains, right? Then nitrogen also promotes tillering. So you can see in the image over there, the wheat plant with tillers around them. Um, and then protein, nitrogen is also important for um, in determining the protein content in grains. All right. Here also you can see an image of the chlorophyll molecule in the microscope and the chlorophyll molecule, the the carbonic chain. But yeah, the formula, I don't know. Yeah, don't say that. But Here you can see the chlorophyll molecule and the chlorophyll in the microscope, and you can see that there are four molecules of nitrogen. There's nitrogen around the magnesium. So yes, each chlorophyll has nitrogen, and that's another importance of nitrogen. Moving on. Well, if you have nitrogen deficiency, then you'll have a reduced grain and head number, which will impact yield. And then if you have insufficient fungicide, then there will be a reduction in the source-sink ratio caused by foliar diseases. So if you're not controlling a fungal disease in your field with fungicides, then you will have foliar diseases, which you will lose lots of leaves, and then the proportion of leaves to grains will reduce. So you will have less leaves promoting photosynthesis, and your plants will have less carbohydrates, less sugars to develop. And of course, this will impact yield. Moving on, so to the objective. The objectives of the study were to identify the agronomic traits associated with genotypic response to intensive management, then to compare genotypes differing in yield potential under standard and intensive management practices, and also to determine if the standard management adopted by producers, by farmers, is appropriate to reach achievable yields. All right, so moving on. General experiment information, which I have to take that general off just a second. Oh man. Yeah. All right. So experiment information. Well, the experiment was conducted at the OSU North Central Research Station at Oklahoma, in the season of 2021 to 2022. The planting and harvest dates were October the 20th, 2021 for planting, and harvesting was in June 14, 2022. The rows were 5 feet long, 5 feet by 19 feet long, so 5 feet wide by 19 feet long. A no-till drill with 7 rows was used, and 2 pounds of nitrogen for each bushel required was calculated for the nitrogen rate. So what this means is, as we can see here, so the yield goal in bushels per acre for standard management was 70. For intensive, it was 100 bushels per acre. So if we are aiming for 70 bushels per acre, then we are doing 2 pounds of nitrogen for each bushel. So that 2 times 70 gives us 140 pounds of nitrogen per acre. All right. We had 6 genotypes, which Butler's Gold, one of the genotypes, was planted twice, one during optimal and the other one during late planted, and the other one was late planted. Here you can see the no-till drill is rolled here on top, planting, and yes, the location of this research station in the state of Oklahoma. Then, all right, so treatments and experimental design. For intensive management, we had only 1 nitrogen application, no fungicide application, and the seeding rate was 60 pounds per acre, which we'll see in a few, but each variety had a different number of seeds per acre because of the different seed size for each variety. So they had all the same weight, 60 pounds per acre, but the number of seeds differed. Then for intensive management, we had 2 nitrogen applications, 2 fungicide applications, and the seed rate was 1.2 million seeds per acre, except for Butler's Gold, which was 1.4 million seeds per acre. Soil test taken at planting with combined depths. So here for total nitrogen, we have superficial nitrogen from 0 to 6 and subsuperficial nitrogen, which is from 6 to 12 inches. And summing both, we have 110 pounds per acre of nitrogen. Then here we have the nitrogen application dates and rates. So during planting, we had It was a 612-0, I believe, NPK fertilizer being ran, liquid, right? Same one we were using this season, I believe. So we had 6 pounds of nitrogen, 6 pounds per acre of nitrogen for both managements, which is not much. Then we had 40 pounds of nitrogen per acre in tillering for both managements, and we will get to the importance of splitting a few. But for jointing, and only intensive management received a second nitrogen application of 50 pounds per acre in jointing. And these rates were applied based on our yield goal that we saw in the last slide, in the past slide. Well, then continue here for the treatments. We had two different seeding rates for standard and intensive management. And as we saw, Buller's Gold Late Planet is the same genotype as Buller's Gold. The only difference is the planting date. Here you can see the planting dates for each variety. And the one from Buller's Gold Late Planet, it was December the 3rd, so during winter time. Here's when you have days with shorter daylight hours. Here you have for center management the varieties, their amount of seeds per acre. Remember that here we have 60 pounds of seed per acre, but then as I said, the number of seeds per acre will differ because of the different seed sizes for each variety. And you can see how Gallagher here has 900,000, more than 900,000 seeds per acre, and it is similar. That is close to it's the variety that is the closest to the amount of seeds per acre that it has in intensive management, which has 1.2 million seeds per acre, as we can see here. And Buller's Gold Late Planet was the only variety here for center management that had 1.2 million seeds per acre. All right. And then for intensive management, all varieties except for Buller's Gold Late Planet had 1.2 million seeds per acre. Then Buller's Gold Late Planet had 1.4 million seeds per acre. Moving on. Then, still during treatments and experimental design, the importance of splitting nitrogen application. So you will ensure that you have nitrogen available before and after jointing. Before jointing, when the first application is done during tillering, the plant is, well, it's growing, right? And most importantly, there is a head inside of the stem being developed, and the number of spikelets is being determined there. So you want enough amount of nitrogen available for the plant, for the wheat plant, for it to give an optimal number, the optimal number of spikelets per head. So that's important. Also, yes, during tillering, there's a lot of cell division, and you need proteins for that. So nitrogen is important for that too. And the second application during jointing, after jointing, is when the requirements for nitrogen and water for winter wheat and for wheat increase exponentially. Okay, I don't know if it's exponentially, but it increases. It increases a lot, the requirements. So you need to ensure that you have enough nitrogen during after jointing, right? And because then you'll have flag leaf, right? The boot stage flag leaf, then grain filling, and then you really want to have enough nitrogen there for these phases, these stages. Then why to split the fungicide applications? Well. So the first application protects the early leaves, so you want them protected, right? And the product that we use here, the Tibacure, is a contact-only product. So what it does, it affects the fungi cell walls. So it does something with the lipidic part of the cell walls where they collapse, and eventually the fungi will die or it will stop developing. Right, because well, their cells have no walls, and it's a 30-day residual time product. The second application is it protects flag leaves and heads. And flag leaves are really important because they determine the photosynthetic capacity, And flag leaves, they're responsible for 75% of the yield, of grain yield. So they are really important. So you want them protected. And well, the heads too, because it's the let's say it's really important agronomic trait too, right? It's where your grains will be. And the second product that we used here was a contact and systemic product. So similar contact, similar to the previous one where it plays with the cell walls, but the systemic one part is where it gets interesting. So what it will do, it will inhibit the cytochrome, and then this cytochrome is in the mitochondrial matrix where oxidative phosphorylation happens. And when it binds to the cytochrome, you inhibit the electron transportation. And when that happens, you are not producing ATPs. The the fungi is able the amount of energy of adenosine triphosphate, the amount of that is significantly reduced for the fungi, right? So it will eventually die, or its development will be reduced, significantly reduced. So that's the way this product works. Then moving on. Oh man, go back. All right, measurements. So sample collection. The above ground biomass was collected in maturity. 1 meter by 1 row. Each row was 7 inches wide. It was collected at physiological maturity. Why is this repeated? All right. It was then stored in a forced air dryer for 7 days, and the whole weight was recorded after that. You can see some photos here. It was collected in between flags, right? Here you can see the clipper used for cutting the wheat. Of course, here is not in at maturity, right? At a physiological maturity, but here was I think a thesis, but it is a picture that I had. Moving on, partitioning. So then after they were dry in the forced air dryer for 7 days, they were partitioned. So heads were separated from the stem. We had heads were counted, heads were weighed, silver weight was recorded, threshing was done, grains were counted, the grain weight was recorded, and chaff it was all recorded. You can see here partitioning, the chaff being weighed, grains being counted. Then the statistical analysis. So for correlation, for correlating the agronomic traits with yield, scatter plots were built using Excel, displaying the square R. Then for the nova analysis, the RBD function was used in the R package XPDS. 3 analyses were done. So the first one was if there was statistical difference within varieties from center management. Then if there was statistical difference within varieties from intensive management. And the last one was to see if there was a statistical difference comparing the yields from varieties in center management versus the same varieties in intensive management. So what we did was we got the difference. So in the yields from intensive management minus the yields from center management, and we analyzed if those differences were statistically significant. All right, moving on. So results. We had a below average rainfall from October to February and April, and 2 freeze events in the month of April. All months from October to February, it was less than the 16-year average total precipitation, and that was bad. We had an extreme drought condition here. April was the worst, where we had a tenth of what was expected we would have of precipitation, and April is critical here because it is whenever leaf boot stage is happening, when the flag leaf is about to come up, when the head is about to come up, a little before grain filling starts. So if you don't have enough water available in this period of time, your wheat, as we saw here in this experiment, in this study, your wheat will be negatively impacted by these conditions. So moving on, we had extreme drought. Here, it's an average from both yields, but this is not the way the 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 way it was said it was analyzed. But here you can see the averages from both yields, from both the average yield for both managements, and they were really similar. You can see that. And moving on, you can see why they were so similar, because whenever in blue you can see the yields, the average yield for each variety in center management, and in orange you can see the average yield for each variety in intensive management. And you can see how little they differ. Green Hammer was the variety that had the largest, the highest difference, right, when comparing its yield in its average yield in center management and its average yield in intensive management. You can see it was the biggest difference. It had the highest difference, and all the varieties they were really similar. They're really similar. That's why we saw that there was no statistical difference, right? Moving on, here you can see that when you consider both managements and you only compare the differences between um, between varieties, you see that Butler's Gold Planet was the only one that had a statistical difference. Right, and we will get to that in a few. Moving on. Here for the results, we have the correlation graph. So here we have above ground biomass, which was the agronomic trait, not considering head weight here, was the agronomic trait that had the highest correlation with yield 0.87 for the square R, an excellent p-value. We have two outliers here, which were Butler's Gold. In every situation here, you have the Butler's Gold always below. Then silver biomass was also pretty close. So square R, for who doesn't know, I believe everybody here knows, but square R shows us how I'll explain a variation. In this case, yield is explained by the variation from another variable, which in this case is above ground biomass. So this is how well above ground biomass explains the variation in yield. In this case, an increase. Then you have head biomass. Also, it was the highest yield, but then you got to remember that grain weight is yield here, and grain weight is part of head biomass. So we are not going to consider head biomass here. But yes, you can see how extremely, but this was expected, how extremely correlated it is with yield. Then average grain weight was not significant. It was negative here. Doesn't explain really well, doesn't explain yield. An increase in yield, right? Then grain number per unit area also explains really well with a 0.8 for square R. Head number explains, but not as well as grain number. Then we have here a summary of the R square values for intensive and center management. And then you can see that above ground biomass had the highest correlation, grain number had a second, and the silver biomass had a third. So here we see how important biomass and grain number is crucial for determining yield. Then going to discussions. Other studies, they found that the panicle diameter affects the grain filling ratio, which affects head weight and yield. So here, yeah, you see another reason why head weight is so connected to yield, right? When you have thicker panicle, you will have more nutrients being allocated to the heads, which will have a better grain filling ratio, and then the heads will be heavier. And that's a really interesting finding here. Then grain number explains better yield differences among genotypes and average grain weight. This researcher here also found this, and we found this here. You can see the values, they're really different. Average grain weight had a really low correlation with yield, and the grains per area, the number, I'm sorry, I forgot to change this here, but the number of grains per unit area was really high, our R square value. Then uh, other studies, such as from Dr. Silva, found a strong correlation between yield and increase in biomass and increase. Found a strong correlation between increase in biomass and increase in yield, as we observed in our study. Then other studies they found a substantial reduction, a big reduction in head weight and straw weight when drought stress happened. Right, this was caused by drought stress. And then other studies also identified a significant interaction between drought stress, nitrogen uptake, and nitrogen use efficiency. So when there is drought stress, wheat won't be taking up enough nitrogen, won't be absorbing not enough nitrogen, and if it absorbs, the use efficiency is low. It is affected, negatively affected by drought. Then here you can see that why Buller's Gold was the late planted that Buller's Gold had a lower yield. Even though we had a higher seeding rate for Buller's Gold late planted, the number of heads, the average number of heads per square feet was the lowest across all other varieties. You can see how it was really low, even compared to this Buller's Gold when it was planted in the normal time. Let's say when it was optimal planted Buller's Gold, you can see that they're the same genotype, but yes, since it had less, it didn't have days with with daylight hours with how can I say that? It didn't have days with long daylight hours. That's what I want to say. So since Buller's Gold late planted didn't have days with long daylight hours, it wasn't exposed to enough sunlight that would give more carbohydrates because of more photosynthesis for it to develop. So then it developed less tillers, right? It had less time to develop tillers because once the cold weather hits, vernalization begins and tillering stops, right? So yes, you can see how it was reduced here. Conclusion. So the increase in grain yield is explained by the increase in most economic traits, as we saw here. Then the most important traits explaining yield improvements were above ground biomass, grain number per unit area, and stover biomass. The adoption of intensive management is more effective when extreme drought conditions do not occur, like seen in this study. So we had extreme drought conditions, and this is probably one of the reasons why we didn't see significant differences when comparing yields in center management with yields in intensive management. They were similar because of the extreme drought that we had. The winter wheat, we believe that the wheat wasn't able to uptake enough nitrogen, and nitrogen use efficiency was really low. So yeah. And the findings of the study can either ways it can still help breeding programs and enhance efficient production systems. Thank you so much for watching. I am open for questions, corrections, anything. Thank you.